Right now, your phone is currently shouting at a cell tower about 3 miles down the road. But in this explainer, we're unpacking the absolute physics of making that exact same phone whisper to a target 450 miles straight up in space and ensuring that target actually hears it. You see, that standard smartphone sitting in your pocket right now transmits at just 200 milliwatts. That is a truly tiny signal. It's a literal whisper that was never ever designed or supposed to be detected all the way from orbit. Part 1, the 180 decibel path loss, the physical barrier to space. To really wrap our heads around the scale of this engineering feat, we have to trace the journey of a single text message or data packet as it leaves your hand. Normally, a standard terrestrial hop is, maybe 3 miles to your local cell tower, but an orbital hop, it bypasses that tower entirely. Your phone's tiny 200 milliwatt signal has to travel 450 miles straight up, punching right through the Earth's atmosphere. And along that epic journey, the signal slams into a massive physical wall known as free space path loss. Basically, this is the severe reduction in the power density of an electromagnetic wave as it travels across vast distances. In this specific case, at L-band frequencies, we're looking at a staggering 185.5 decibel loss. To put that into perspective, it's literally like trying to hear a pin drop in a hurricane from the next town over. Part 2, giant ears in orbit, solving the hardware problem. Obviously, you can't just slap a 10-foot satellite dish onto the back of your smartphone to fix this, right? So the solution is entirely inverted. Instead of putting a massive antenna on your phone, engineers like those at AST Space Mobile are deploying colossal space towers in orbit. Once their BlueBirds satellites reach low Earth orbit, they unfold these incredibly large flat panel antennas, essentially acting as giant, highly sensitive listening ears in space. Looking inside the clean room really shows you the sheer scale of a Block 1 micron array. It's an enormous 693 square foot phased array. And that massive surface area isn't just for show. It is strictly necessary to provide the immense signal gain required to actually catch your phone's 200 milliwatt whisper. And the engineering is scaling up rapidly. Those 693 square foot Block 1 arrays, that's just the beginning. The upcoming Block 2 satellites are designed to be over 3 times larger than that. At that kind of scale, they aren't just catching simple text messages anymore. They're actually beaming two-way broadband data directly to perfectly normal, unmodified phones. Plus, a single one of these satellites covers a footprint the size of Texas. Part 3, catching a speeding bullet. The Doppler shift challenge. So, having a giant antenna is incredible. But it simply isn't enough when your new cell tower is essentially a speeding bullet. These low Earth orbit satellites are hurtling across the sky at roughly 7.5 kilometers per second. That extreme orbital velocity generates severe Doppler shifts up to 40 kilohertz. If you tried to connect a normal 4G or 5G signal to something moving that insanely fast, the terrestrial protocol would instantly be confused and just drop the connection completely. Part 4, tricking terrestrial protocols. The software heist. Since our standard 4G, LTE, and 5G protocols were built for stationary towers planted firmly in the ground, engineers had to design some brilliant software workarounds to literally trick these protocols into functioning across orbital distances and hypersonic speeds. One major part of this trickery is timing advance. Because a satellite is flying overhead so fast, the distance between it and your phone changes by the millisecond. This causes rapid propagation delays, varying by about 20 microseconds every single second. So the system has to aggressively and continuously calculate predictive timing advances just to keep the connection synchronized. Now, to manage all these extreme physical variables, the industry is actually fractured into 2 distinct architectural paradigms. On the left side, we have the direct-to-the-cell, or D2C approach, which handles the Doppler shift purely on the satellite side. And over on the right, the standardized 3GPP non-terrestrial network, or NTN approach, which uses joint compensation. So the absolutely crucial point of the D2C method is that it pre-compensates for the physics. The satellite itself uses orbital data to predict the Doppler shift and literally pre-distorts the signal before it ever leaves space. The magic here is that this allows the signal to be perfectly compatible with the exact, unmodified legacy smartphone you already own. The trade-off, though, it sacrifices a few decibels of link margin to pull this off. Conversely, the standardized NTN framework takes a collaborative approach. The satellite broadcasts its velocity data, but it requires a specialized NTN-aware phone down on the ground to calculate the fine estimation. By sharing that tracking burden, this method yields a highly synchronized, coherent link with a vastly superior link margin, which is, absolutely essential for data-heavy next-generation tech, like autonomous driving. This creates a really fascinating trade-off. D2C gives us unmodified handset compatibility, which is amazing for immediate universal emergency coverage, but NTN provides a better uplink margin, around 10 to 12 decibels, and drastically lowers routing latency, down to between just 25 and 60 milliseconds. It's a highly optimized framework designed from the ground up for massive 6G scalability. Part 5. The TriLink future. Weaving the space web. Now, these two approaches aren't necessarily competing realities that are going to just cancel each other out. As these massive BlueBird arrays continue to unfurl in orbit, and as those 3GPP standards evolve, these two architectures are actually charting a course toward a unified network. The future isn't about giant space antennas completely replacing terrestrial cell towers. It's about a 6G convergence, a hybrid TriLink architecture. In this model, terrestrial 5G handles your dense urban infrastructure, the standardized NTN handles high-throughput broadband directly from space, and D2C serves as your universal, unmodified emergency and rural fallback. They all operate seamlessly together. Which brings us to the ultimate implication of overcoming that massive 180 decibel path loss. With absolutely massive orbital hardware and brilliant protocol trickery, finally conquering the physics of the 200 milliwatt whisper. When every single standard smartphone inherently doubles as a node in an invisible planetary space web, does the concept of a dead zone simply cease to exist?